Part 3. The CPU, the central processing unit that will organize everything. We'll see about the building blocks of the CPU necessary. We'll speak about operations that it can make, how they are organized. We'll see the memory. We'll see differences between CISC, complex instruction sets, and RISC architectures. We'll see instructions. We'll see arithmetic logic unit, how it is built, what are its features, and so. We'll see then, after this, the pipeline, why it is important, and how to use it. The CPU, as it is the brain of your system, is what will manage everything that you have inside your computer, your microcontroller, and so on. It is designed to do several different tasks very well. The basic principles actually are kind of old, but very well proven. In fact, if you see the documentation, for example, for the Z80 even, you have something that is relatively modern that you can understand and you can play around with FPGA and everything. Your CPU is composed by at least an arithmetic logic unit, a control unit, and register, most importantly. You can have also some cache and some extra features, but except for the cache, you will know it's not guaranteed that you will find everything. The CPU, it will work. We will work by accessing data, reading or writing data. You will decode instructions, you will need to understand them, you will need to execute these instructions and make, of course, operations, whether it will be logic or arithmetic. You have that when you execute an instruction, the instruction will be a data, a byte, 16 bytes, a long word, anything. The CPU will, of course, need to do the instructions. These instructions are by themselves data that will need to be understood. The cycle in which you take the instructions, read them, and do them is called fetch, decode, and execute routine that is implemented by every CPU. First of all, you fetch from the memory one instruction and also data operands. So you access the CPU, the CPU asks to the memory, the data that you need to operate with will be put inside a specific bus that will transport this data to your CPU. The CPU will take this data and then the CU will take it, will read it, and will understand what it needs to do after. So it will activate several parts of the circuitry that will do your job. After the CU has decoded and understood your instruction, it is then job of the arithmetic logic unit to perform your actual instruction. It will work with the data and some specific registers to do exactly that. Then, after you have the result, you can store it. This is a more specific, more precise routine how it is performed. So you have instruction fetch, instruction decode, operand fetch, instruction fetch, and the result to be stored. The memory access is a very important part of your job. Of course, the CPU will work with data, so you need to be able to read all of this data. From memory, they will say RAM, your hard drive, and so on. The memory usually is one of the biggest bottlenecks of your system, because the memory is inherently slow. You have CPUs that go fast, gigahertz time, but it's not the same thing for your memory. Strategies that you can implement to have better performance through memory, and it is actually usually parallelizing and having the data more local, so which is cache. For the parallelism, it means you are using more buses and also wider buses to transmit more data at the same time. It means that we switch, for instance, from von Neumann architecture, which everything is as one bus, to our hardware type architecture, which have at least one bus for data, one bus for instructions. Nowadays it is maybe a little bit more complicated than this, but the basic principles remain, so you can understand it. We have two types of CPUs with independence to the CPU. In fact, it is a finite state machine, of course, that can be like complex or very simple. It is a complex FSM if it is like a CISC device, CISC CPU, complex instruction set computer. In this case, both the instruction, the time to perform an instruction and the time to decode an instruction is not the same. It is not always the same, it's not fixed. In the case of that instruction set, you can do maybe less complicated things than a CISC one, but you have the guarantee that each instruction will take exactly one cycle, which is very important. One thing about this kind of machines is that actually for like practical needs they started appearing after like where you had word type of data, like so you have 32 bits, 16 bits. You cannot, it is hard to have like some kind of machine like that with 8 bits, of course. But they are very interesting because they are fast, usually much faster. In fact, you have different instruction set architectures that can follow the directives, that can follow the RISC type or a CISC type. CISC type could be like x86 and its flavors, could be RISC type, for instance, ARM, RISC-V, and so on. Usually you see that you still use the x86 type of processors, even they may be less performant than the ARM type processors. But this is of course because you have a very nice infrastructures, which is also the reason why like ARM is also nice, because they have also them a very nice infrastructure that they have built during the last years with Apple and so on. Your instructions are by themselves data, a number that needs to be decoded. There is you can theoretically program with these numbers if you are super brave, but there is one step that is more possible to work with, which is called assembly code. So it is a code that is like you write on your keyboard, and there is a direct relationship between the machine level code, which is numbers, and this code assembly. And ideally, of course, you have when you have like a higher level, like your C code, you don't do the translation from the C code to the machine level. That's yourself, of course, but you have interpreters that translate everything in your C code into machine readable code. You have that this one, in fact, is usually much better than what you can do in this kind of situations. Maybe it can be useful to touch with this code, like change a little bit by yourself, but usually it might not be worth the effort. The arithmetic logic unit will take the instruction and it will perform it. It will be able to take several inputs from several registers inside a CPU, and it will be able to give outputs in several registers again and then also it will operate in the status register, which is a special register that will contain some flags that can influence the work of your CPU. The arithmetic logic unit is different, of course, in respect we're speaking about CISC type architectures. on RISC-type architectures. Arithmetic logic unit in the SISC-type architecture is more complex, of course. As I was saying before, it will do something, when it does something, it's not guaranteed that it will do it in a specific amount of time. It can last longer, depending on the instruction, so it's more complex. Instead, also, the RISC-type architectures, especially in longer types of words, can do more interesting things also. For instance, ARM instruction set makes possible to put in several instructions an if condition with some bits on the status register, for instance, immediate operator, and so on. For instance, you might find that an add function we can make possible to add a specific number on the instruction immediately. So you can say like take variable c, add 2, and it will do it in just one instruction, while it can be more difficult in other architectures. Let's see again what happens when you do one instruction. You see that, for instance, we have an instruction add one number to another one. Very easy. What will happen is that initially we have the data, let's say, ready to be performed, like it is in the bus, or better again, in one register, so we can access it in just one clock. We get instruction, one clock will pass, then we need to decode it, which can take another clock, especially in SISC-type architecture. It is a different step. It can be the same step in RISC. Then it needs to fetch the operands, which is again at least other one clock cycle, and then again it will perform the instruction, again another one if you are lucky, and then it needs to store the result. If we need instead to take data, move them, it takes longer. So if we need to move data from one register to another maybe, and then perform the addition, it will take 3 times as much, so in total at least 15. It will not be the same. It is a very simplified case, of course. It will be worse. If you do one instruction and then wait for it to end, and then do another one, you are using the hardware very bad. It's not good. You need a way to parallelize the instructions that you are doing. Because when you do one instruction, since part of it is done by a specific part of the circuitry, you want to be able to use it all at the same time to be able to do more and effectively pretty much the same energy. In this case, you want to perform what is called as a pipeline. The pipeline is in fact the technique that you use inside the CPU itself. You don't have to program for that usually, and you use to parallelize the instructions that you are doing. It's in a SISC-type CPU, since it's not guaranteed that everything will take just one TC time. It is very hard to do pipelining. It can be challenging. You need to forecast what will happen. So it's like all of these dogs. It's not very cool. Like one is longer, one is shorter. You need to pile them nicely. No, it is hard. But in RISC type of applications, since everything takes exactly 1 TC, 1 per times TC, it is easier to forecast what will happen. The consequence, you don't need like wizardry circuits to do that. So the pipelining, it is more easy to do and more efficient.